Hello everyone, welcome back to Explore Electronics. In this video, let's see the new question paper released by VTU, that is Basic Electronics BBEE103/203 subject. So let us solve the model question paper and let us look at the solution for these questions. In the model question paper, from module 1, these are the questions. They have mainly concentrated on the PN junction diode and Zener diode and a rectifier. So in the first question, they have asked to explain the forward and reverse characteristics of PN junction diode. When we are forward biased it, how actually the diode is going to behave. This is forward biasing of diode. This is reverse biasing of diode. And here is I have given the explanation for forward biasing and reverse biasing and how actually the diode is going to work. Mainly in forward bias, you need to say diode is on and it is going to conduct the current. And here in the reverse bias condition, diode is off and it will not allow to flow the current, means diode is off. And you need to explain this characteristic curve. This is forward biased condition and here it is reverse biased condition. Here you need to mention the V knee point, means that is 0.3 volts for germanium diode and 0.7 volts is the cut-in voltage for silicon diode. From here onwards current is started to flow. And similarly you need to mention the reverse breakdown voltage and the leakage current flowing in the reverse condition. This is about PN junction in forward and reverse bias. Here is the problem on Zener diode. They have given the source voltage which is varying from 20 to 40 and the breakdown voltage of the diode is 10 volts, and also they have given the input resistance, that is 820. We need to find out the minimum and maximum Zener currents. So this problem solution is explained in the next video. This is what the thumbnail of that next video, solution to problems. You can see the solution over there. With neat circuit diagram and waveform, explain the working of bridge rectifier. So you need to write the bridge rectifier circuit first. You need to write it clearly. From these 2 points, if you start writing the diodes, it will be in this direction. Remember this rule. These 2 points you need to take. One diode will be in this direction, next diode will be in this direction. Similarly, you need to go in this way. One diode here, another diode here. Then only this circuit will be correct. If you are going to place these diodes reversely, this circuit will not work. So you need to explain this construction of this bridge rectifier, and when positive half cycle of the input is applied and negative half cycle of the input is applied. And explain how Zener diode is used as a voltage regulator. So for this question, you need to write the circuit of voltage regulator using this Zener diode. Remember, this Zener diode is connected in reverse biased fashion. You need to mention that. And the answer for this question is, you can explain using no load and full load conditions, or else you can explain using line regulation and load regulation. So here it is not mentioned to explain no load and full load or line regulation and load regulation. You can explain in any way. Here I have given both. For no load condition and full load condition, these are the current expressions. If you consider line regulation, here line regulation in the sense V in varies, means this is variable and RL is constant we need to take. In such condition, these are the expressions we are going to get, variation in the currents. And in load regulation in the sense we are going to vary RL and V in is keeping constant. In such case, these are the variations in the current. Here the main thing is that how actually this IZ compensates the total current. Here we need to explain here also how this IZ increase or decreases accordingly, and it will compensate for the maximum and minimum current flowing through the circuit. And explain with the neat diagram waveform working of half wave rectifier. This is the circuit of the half wave rectifier. This is the input wave we are going to apply. We are going to get the output as like this. This is the rectified output of the half wave rectifier. And you need to explain what happens when we are going to apply positive half cycle of the input and negative half cycle of the input. And also they have asked in the question to derive the expressions for efficiency and also the ripple factor of the half wave rectifier. You can see here, this is the derivation for the efficiency. This is the derivation for the ripple factor. Here IRMS is used. So to get how actually the RMS value is going to be calculated, you can refer this, or else you can neglect this part, means RMS value calculation. You can directly go with ripple factor expression and also efficiency. Why? Because this question is asked for only 6 marks, 7 marks. Here it carries 4 to 5 marks for the rectifier explanation and 2 to 3 marks for the derivation. So no need to derive the RMS value also completely. Directly go with the ripple factor and efficiency derivation. Again, this is the problem on full wave rectifier. It is given as 30 volt transformer is used. Here is the load resistance and the diode forward resistance. We need to calculate the average load current, average load voltage and rectifier efficiency. Let's see in the next video. And then coming to module 2, you can see here module 2 is on BJT. Common emitter configuration is asked here. And then MOSFET explanation, working and construction, and BJT various currents and voltages. And again coming to biasing, and then N channel JFET also asked, and relationship between alpha and beta. So if you see common emitter amplifier configuration, we need to explain input and output characteristics. So this is the circuit which I have written using NPN transistor, and this is the input characteristics, where in input characteristics we need to take input current, that is IB, versus input voltage, that is VBE at the input side. Similarly, output characteristics means IC, that is the output current, with respect to the output voltage, that is VCE, in between collector to emitter. This is how we need to write the characteristics. And in the input characteristics, we need to keep the output voltage VCE constant by assuming VCE at this 1 volt or 10 volt. This is the curve. Similarly, for the output characteristics, we need to keep input voltage for a constant values like this, and we need to explain how the behavior of the amplifier is. Up to this, it is increasing, means the current is increasing. From here onwards, the current will be constant. So you need to explain saturation region, active region and cutoff region. And then coming to the next question, it is on N-channel enhancement type MOSFET. So these are the 3 regions of MOSFET operation. First, you need to explain here the construction. How it is constructed means we will be having an P substrate. Within the P substrate, there are 2 N regions are connected. Above that, there will be an SiO2 layer. Above that, there will be polysilicon layer. This will be act as gate, this will be act as source, and this will be act as drain. And the voltages will be VGS with respect to source and VDS with respect to source. You need to explain the construction first and then coming to the working. And also here the characteristic is given, ID characteristics, ID versus VDS, and also you can explain how the saturation, non-saturation and cutoff currents are going to be. Explain various currents and voltages flowing through the BJT transistors. Here current and voltages means IC, collector current, IB, base current, and IE, emitter current. First you need to write this expression, and also you need to write where are the voltages, VBE, VCE we are going to consider usually. So this is PNP transistor is concerned, this is NPN transistor is concerned, this is IB, IC and IE. So if you see this NPN transistor representation, current going outwards from the emitter terminal. So this is IE. Similarly, if you look at this, these 2 currents are coming inside. Similarly, in PNP transistor, current is going inside from the emitter. So this is IE, and then it is splitted as collector and base currents. Then explain transistor biasing circuits with relevant expressions. Here they have not given particular biasing. So I have explained both fixed bias or base bias circuit with the expressions. We need to apply KVL to the base and collector circuits and write the expressions for voltages and currents. And also voltage divider bias I have explained here. So out of these 2, you can write any one biasing if they have asked for some 4 to 5 marks, but here it is asked for 7 marks. So better to write 2 types of biasing with explanation. Then make use of N-channel JFET to describe its operation and characteristics. This is the N-channel JFET structure. Here again within the N region we will be having 2 P regions, and we will be having a gate over here, and you need to explain the construction and then operation coming with no bias voltage. There is no voltage applied to gate, and with respect to the negative gate to source bias voltage, and this is the ohmic region, saturation region and the breakdown region, and also the cutoff region you need to explain. And define alpha beta, determine the relationship between alpha and beta. Here first we need to write what is alpha and what is beta. Alpha and beta are amplification factors in common emitter and common base configurations. But coming to the transistor, these two alpha and beta are with respect to the currents are considered, that is IE, IC and IB. So taking this expression into consideration, we can derive the relationship between alpha and beta. So if we divide these three by IC, here IC get cancelled. So we know that alpha is equal to IC divided by IE. So this term becomes 1 divided by alpha and this term becomes 1 divided by beta. So this is the relationship between alpha and beta. Alpha in terms of beta. Here if we take this expression and rearrange for beta, this is the expression for beta in terms of alpha. So this is the very important question again. This is for 6 marks. So you need to write this expression, what is alpha and what is beta. You need to explain in words also. Then coming to module 3. Module 3 is of op-amp. Here the questions are on ideal characteristics and also there is a problem and then integrator, differentiator. Similarly in question 6, the choice question, integrator, differentiator is repeated. You can expect differentiator also. So you can expect differentiator over here. There is one problem again. Usually problem will be on summer. This is also the problem on summer circuit. And again they have asked summer circuit. So this module is very easy. You can score good marks here. Briefly discuss the ideal characteristics of op-amp. So these are the ideal characteristics of op-amp. Here I have given practical values also. In exam you may get question like explain ideal characteristics and also the practical values of those. So here other than writing the table, you need to explain the output, the open loop gain is infinite and input impedance is infinite, means at the input side resistance is maximum, output impedance is 0. Similarly offset voltage is 0 in the ideal case and slew rate, bandwidth, CMRR. You need to explain these briefly. 1 line or 2 line of explanation for each and every one is expected in the exam. Design the circuit diagram. So this is again a problem. The solution is given in the next video. This problem is also on the summer circuit. So there are 3 voltages given with these weights. So let us see the solution in the next video. Derive the expression for integrator and differentiator. So this is the integrator circuit. Here we will be having R and C. Rin is the input resistance. In place of a feedback network, we will be having a capacitor. This will be act as integrator circuit. So here I have taken In and If. Again these two are equal. Why? Because current flowing into the op-amp is 0. These two are equal. So derive for In and If, current through the resistor and current through the capacitor, and equating those two you will be getting this expression. And here we are interested in getting integration of Vin. So if we take integration both sides, we will be getting this expression finally. This is integrator output. In the similar way, we can derive the expression for differentiator also. Differentiator is that at the input side we will be having a capacitor and feedback network will be having a resistor. Here also In and If are equal, and if you write If expression, it is minus V out by Rf. If you write In expression, current through the capacitor is this, and again comparing or equating those two, we will be getting the expression for V out. You can also write it as V out is equal to minus Rf into C dV in divided by dt. And here again the problem. This is also on the summer circuit. So you can easily expect one question from the summer circuit. Let's solve in the next video. Again the question is repeated here. Derive the expression for integrator and differentiator, which I have already explained in the previous question. Let us skip this. Now derive the expression for 3 input summing circuit. So 3 input summing circuit means we need to have V1, V2, V3. Accordingly we need to have the input resistances R1, R2, R3 and a single feedback resistor RF. In the same way how we have derived integrator and differentiator, here also first we need to write the expression for I1, I2, I3 by taking V1 as this point voltage, and here Vx we can consider. This Vx will be 0. Why? Because this terminal voltage is 0. Because of virtual ground, Vx will be equal to 0. So we are going to get the expression for I1 as V1 minus Vx divided by R1. but here Vx is 0, it becomes V1 by R1. Similarly I2 and I3. So IF is equal to these total currents flowing over here. That's why IF is equal to I1 plus I2 plus I3. Equate these, finally we are going to get the expression for V out like this. And again module 4 is of digital part. So here some conversions will be there. This question is for sure with different values. One type of conversion they will ask. And implementation using NAND gates and NOR gates is asked. Full adder, De Morgan's theorem, and problem on subtraction using ones and twos complement method. Half adder with logic diagram and the truth table. Let us see. Again I have solved this conversion in the next video. And here is the expression given equation y is equal to AB plus CD plus E. Once you get the expression like this and we need to implement it using NAND gates or NOR gates, what we need to do, usually NAND gate expression is A into B whole bar and NOR gate expression is A plus B whole bar. Means finally we are going to get the expression in terms of whole bars, right? So we need to take the double bar into consideration. We need to take the double bar for the expression given. What happens if we take A double bar? It is A again. So this expression will not change if we take the double bar. And try to solve one bar first. Keeping the one bar as it is, we need to solve this one bar and we need to split this using De Morgan's theorem. If you take this double bar and solving for one bar using a De Morgan's theorem, it becomes, this term becomes AB whole bar, this plus becomes product, that is dot, CD whole bar into E bar whole bar. So now if you see this, this is one term into this is one term into this is one term, will be having whole bar. So this is in the form of NAND gate expression, A into B whole bar, right? So we can easily implement this in a NAND gate fashion. So this is using NAND gates. Okay, then coming to the NOR gate implementation, you can see here, this again I have taken in the same way, taking double bar and simplifying for one bar, we will be getting A into B whole bar into C into B whole bar plus E into E bar whole bar. But this is the type of NAND gate implementation. Again what we need to do, we need to simplify the inside part, A into B whole bar. It becomes A bar plus B bar into C bar plus D bar into E bar. So here what happens, this is in terms of NOR gate implementation, but we will be not having a complete bar. So again I am simplifying this. So we will be getting A bar plus B bar whole bar plus C bar plus D bar whole bar plus E. Here double bar get cancelled. Now this can be implemented using NOR gates. But here I think one more NOR gate is required. Please cross check this. I have done it wrong. One more, why? Because it gives Y bar, I think. Here one more NOR gate is required, or this is sufficient. Please check and comment below in the for the video. Next, construct and describe the full adder with neat logic diagram and the truth table. This is full adder. First you need to write the block diagram and then truth table. By looking at the truth table, we can generate the expressions for sum and carry. Here I have given the detailed explanation or simplification for sum. If they have asked for less marks, if they have asked for only 4 to 5 marks, you can directly write these expressions and implement it using the gates. But here it is asked for 7 or 8 marks. If they ask, better to show the simplification also. This contains marks. So this is the logic circuit for sum as well as carry. State and prove De Morgan's theorem for 3 input variable. 3 input variable means we need to take A, B, C into consideration. If they have asked only 2 input variables, show for A into B whole bar will be equal to A bar plus B bar, like that. Since it is for 3 variables, take 3 variables and show. You need to write the expressions and also you need to write the statements clearly as it is, and then using the truth table generate A, B, C values and A bar, B bar, C bar, and here we have required A bar plus B bar plus C bar. So here is A bar plus C bar plus B bar term, and also A into B into C whole bar and A bar into B bar into C bar and A plus B plus C whole bar. Then you can show like this, these two are same and these two are same. This is how we can prove the De Morgan's theorem. And again, this is a subtraction problem on 1s and 2s complement. Let's see in the next video. They have asked half adder with neat logic diagram and truth table we need to describe. This is the block diagram of half adder, truth table, and also sum and carry. And one more thing, observe here, they have just asked the logic diagram, but they asked to implement using basic gates. This is the circuit using basic gates. Here I have used only basic gates. Otherwise, you can just use a simple XOR gate for getting sum for AB and use A into B one AND gate, you will get carry, right? This is the simplest circuit we can write. But if they ask to implement using basic gates, then you need to write this circuit. Then module 5, explain potentiometric type transducer. Here is the problem. Let us solve in the next video. And then what is define modulation and need for modulation, and LVDT, again one more problem on capacitive transducer, and then communication block diagram. This is the potentiometric transducer. Here you need to show if this shaft is going to vary, how the difference in A and B values or the voltages. You can show with this diagram also. If this strip varies, here R2 resistance varies and V0 is going to vary. You can write other circuit or diagrams also if you know with respect to the potentiometric transducer is concerned. And this problem on strain gauge, let us solve in the next video. And coming to modulation, define the modulation and explain the need of modulation. Here we need to write the modulation definition first clearly, and then write a block diagram like this. No need to show all these three waveforms, you can show any one. And need for modulation, you need to explain these points clearly. At least write 1 or 2 points for this, how it will reduce the antenna height, and we can allow mixing of signals, range of communication improves, multiplexing is possible, and improves the quality of reception. This is about the modulation and need for modulation. And the last question, that is 10th question of module 5, explain LVDT with relevant diagrams. This question is also asked multiple times. So you need to write the diagram like this, and also if you have a cross-sectional cross-sectional diagram, you can also write that. Here also you need to clearly explain when displacement happens, how the voltage at ES1 and ES2 varies when there is a moment in the core, that is displacement. You need to explain the mutual inductance here clearly. And again, problem on capacitive transducer. Let's see the solution in the next video. And the last question is, describe the blocks of basic communication system. These are the blocks of communication system starting from information source to destination. Here is the input transducer, here is the output transducer, this is transmitter, this is receiver, in between this is a channel. And here remember, noise will be added up to the channel. Don't make a mistake while writing. This is noise added up to the channel, arrow mark should be towards channel. And you need to explain in brief what are all the things happen in each and every blocks. Transducer will convert the physical quantity into electrical quantity. Electrical signal will be called as a message signal, and transmitter do the modulation. So we will be getting a transmitted signal, that is modulated signal, that will be given to the channel. Channel can be a wire or it can be air medium. And then there will be a receiver where demodulation happens. Here the carrier is removed, and output transducer will convert again the electrical quantity into a physical quantity, and destination. This is what you need to explain for the different blocks in the communication system. This is about the theory questions in this model paper. In the next video, let's see the solutions also for the problems asked in this model paper. Thank you.